and I decided that the world was big and Holland was not quite so big. So I went to the US to do a PhD and ran into an Australian girl, and so that's how I ended up in Australia. And this is in fact the first time I've been back in Holland to do something professionally. So it's really fun for me. So what I wanted to do today is talk a little bit about slow light in nonlinear optics. Then I have a few slides in my capacity of editor-in-chief of Optics Express at the end, to tell you a little bit of what's brewing and cooking there. As Marco was saying, I'm with the School of Physics at the University of Sydney. I mean, these triple affiliations are always messy. IPOS is merely some organization of all the optics people at the University of Sydney. So that includes us in physics, the electrical engineers, and some of the chemists. Kudos, Marco was saying earlier. Let me just tell you a little bit about that. So that is it's an international collaboration funded by the Australian Research Council, the ARC, and it involves 7 universities in Australia, in the cities of Melbourne, Sydney, and Canberra, who get all the money. And it has 15 chief investigators from those universities in Australia, plus 15 from elsewhere in the world, including co-Skypers from this place, which is how I got to know some of the students here. The funding we received, I should say, we were established in 2003, got 8 years of funding, which ran out. Late last year, the government put in a new program where we were lucky enough to get funded again for 7 years. Funding is about 27 million Australian over 7 years, and $1 Aussie is about 3/4 of a euro. On top of that, we get some matching funds from universities. So it is really quite, once you have one of these centers, I wouldn't say that life is comfortable, but at least you don't have to worry on a day-to-day basis about funding, which is comfortable. The themes of this new center, I can just flash the words here. I won't go into them in detail, but I'm happy to talk about them afterwards. Quantum integrated photonics, integrated mid-infrared photonics, terabit per second communications, nanophotonics, of course, you guys do that here as well, and hybrid integration. And I guess the last point I wanted to say is that we are hiring. My colleagues now in Sydney just hired 5 people. We will be hiring more. Our colleagues at these other Australian universities are hiring and will do so in the future as well. Sydney is a lovely place, and some of the students actually live close to the beach. Though regrettably, if you have to buy a house, you don't. All right, I've been very fortunate in having very good collaborators, mostly students, some people from some colleagues from established places elsewhere. The work I'll be talking about today was done by PhD student Joe Mock and a visiting student Falk Eilenberger from Jena. He got a fellowship to come to Australia for a year, all expenses paid, and he had a ball, and so did we, because he's a very good student. So rather than talking about what we did last week or even last month, let me tell you our work in the area of nonlinear slow light, how it has developed over the last couple of years. So I'll start with some work which we described in the 2006 paper, and then I'll work on, and the last results I'll show you were done in October last year. Right? So it's a nice to have the opportunity to talk about a kind of a research area. Okay, now, many of the experiments we do, though certainly not all of them, are done in fiber gratings, and let me tell you what they are and then why we like them. So optical fiber is a cladding, which is pure silica with a core, which has a slightly higher refractive index because it's doped with germanium. Germanium is lower in the periodic table, there's a few more electrons, so its refractive index is slightly higher. Now this germanium doped silica is photosensitive, which means that if you put UV light on it of the right frequency, then the refractive index changes a little bit. It's a complicated process that nobody really understands, but it can be controlled, and the refractive index change is about 10 to the minus 3, 10 to the minus 4, very, very tiny. Okay? Now, what is done to make these fiber gratings is that you have two interfering plane waves of this 244 nanometer light, which gives you a sinusoidal interference pattern in intensity. And then by this photosensitive effect, the holography refers to that, you burn, if you wish, you burn a refractive index distribution of the same sinusoidal shape into your fiber core, and that's your fiber grating. It's very, very weak, as I mentioned, 10 to the minus 3, 10 to the minus 4 index contrast, but you can make them really, really long. Ours are 10 centimeters long, the period is about half a micron, so you have 10,000ths of periods. Okay? Now, the experiments in these fibers are relatively easy. The fabrication technology is relatively easy. It was developed for the telecoms industry in the late 80s and early 90s, and we run piggyback on that, so to speak. Okay? You miss the full richness of photonic crystals, and we have done work in those as well, but I will not talk about that today. But it has some of the essential features, namely Bragg reflection, right? This is a periodic array of a periodic refractive index distribution, and therefore you get Bragg reflection, and you get an associated band gap. Okay, it's just a one-dimensional band gap. Okay, now let me just give you a couple of the relevant equations. In the simple one-dimensional system with low index contrast, the expression for the Bragg frequency is given by pi c on n d. N is the average refractive index here, d is the period. Okay? The second equation that you need to know is where the nonlinear optics comes in. Now there's saying that something is nonlinear is like saying that that wall there is not red. It's a negative statement, right? Everything that's not linear is nonlinear. It doesn't tell you very much. The particular nonlinear effect I'm after here is the Kerr effect, which all optical materials exhibit to some degree. And it is the effect that in one of its manifestations gives you a linear dependence of the refractive index on intensity. Okay? And the N2 in glass that I'll be talking about is positive. So the refractive index during the day in that window is slightly higher than it is at night. Now the effect is pathetically weak. We're talking 10 to the minus 12 probably or so. But if you have very high intensities and you have long optical path length, the 10 centimeter I was talking about earlier, then that can accumulate and you get visible effects. Okay? So, oh, sorry, and I should explain this figure. This is a schematic of the transmission versus frequency of one of these fiber gratings, right? The transmission is unity or very close to unity for most wavelengths, except at the Bragg frequency, where the light is reflected by Bragg reflection, and a very narrow range of frequencies around it. And the width of that range is about the 10 to the minus 3, 10 to the minus 4, associated with this refractive index distribution. It's just, apart from a factor 2, those two are the same. So we have this very narrow region of low transmission, high reflection, and the rest is strongly transmitted. And now what happens when I'm going to crank up my intensity? That's the question that I, just as an introduction, want to answer. Well, you look at this and you say, well, my refractive index goes up. That probably means that my Bragg frequency goes down. And so what you might expect is that these guys, that this whole thing moves to lower, to lower frequencies. Okay? Well, so what, now let me just to kind of set the scene a little bit, show what that means, show what you measure experimentally. Here you might expect that if you sit at a particular frequency that was in, say, here,